We were looking other day about the maximum frequency at which a amplifier or an analog circuit can function, and we gave a concept of what we call as the figure of merit frequency, which is essentially called FT, okay. And we did derive, or at least showed you, that typical FT is Gm by Cgs, related to Gm by Cgs, and if I put the values please. So concept of a figure of merit frequency which is called Ft, and we defined it by saying that it is equal to Gm by Cgs. The Cgs term is essentially coming from input capacitance. If there is any additional capacitance, it will be Gm by Cin actually, okay, but right now I am only using Cgs. So for a device it is only that capacitance which I have written, but for external circuit it may have some more capacitances there. And if I write this transistor Ft, which is 3 by 2 pi mu by L square BOV, typically this may be much higher than gigahertz, tens of gigahertz, typically it may be as high as 100 gigahertz. And we always say that the concept of the maximum frequency at which a circuit can function relatively correctly, or you can say correctly means our modeling which we did is based on the lump models of the device, is valid at that point. We discussed last time that typical frequency could be 10th of the Ft. Now this is the other method I suggested, that okay, you can take a geometric mean of the pole frequency and the FWT and it may come close to the value of 10th, okay. So it is not that either one is wrong or right, it may be little more accurate than this, but 10 is good enough approximations. We also discussed that day, apart from this is what we did, I am just trying to recapitulate. In the Ft evaluations we always see that we used a model which is called large signal or large channel model, a long channel model for MOSFETs, and there we say that larger the VOV as the function shows, Ft will be larger. However, this was assumption that device is always in a reasonable inversion, but if it is in very strong inversion or a very weak inversion, these assumptions are not valid, and therefore Ft relationship with VOV is suspect. In fact, the problem starts now that whenever you actually go down to short channel devices, okay, the definition of short channel device also varies from people to people, and device people have some other way of telling. But for you can take from me, a short channel device is called short channel, I mean a MOSFET device is in short channel if the channel length is of the order of the depletion layer widths, okay. If it is in that order, then we say you have in a short channel devices. Or if you are a technology minded person, typically similar scaling is done for all length and widths. So one can say if the channel length is some way a similar numbers like the junction depth of the source and drain, then you are also in short channel. So this is a definition which is arbitrary to some extent. The major thing which we will see in a short channel is okay, and that actually changes the other parameters. There are many short channel effects, some other course they should learn about it. There are n number of things which you can talk about. From the circuit point of view, my worry is EY is now stronger, and I kept on saying Ex is too strong compared to Ey, which may not be now valid, they may be comparable. So both fields may cross, there will be effect from both sides. So there is this short channel word is only, as I say, is a definition, and take it in reality whatever the experimental result shows, that is the short channel. Typically one can say 0.35 micron or even 0.5 micron device can be said to be in short channels. So most of the analog circuits are now actually working on short channel devices, but with the digital technology going to 90, 45, 65, 45, 22, 16 nanometers, you are really going into short and shorter channel devices, and the worries will become even much more than what we actually saw at 0.25 or 0.18. Okay, so this fact that we have looked into Ft, that in a short channel the relationship between Ft as well as Gm by IDS is a little suspect, okay. So one should not really go too strongly saying that VOV is a good parameter of design, which we have been talking very casually or that's the end of it. Once I know this I can do everything. But in reality this is not the best parameter of a design. Okay, so we will come back to that part again, but here is some two figures which makes my point clear. If you are, the point which I am now making is interesting. For a MOSFET amplifier therefore two parameters decide the performance. One is GM by IDS, the other is GM by CGS. Okay. Now if we, that is the expressions I wrote, that is what point I am trying to prove again to you. If I plot GM by IDS against VOV and I also plot GM by CGS against VOV, two, you said these are two figure of merits, okay, so I plot as a function of VOV. You can see the GM IDS is inversely proportional to VOV, so it actually shows some, more accurately it does not follow linear, it should look linear but it is not linear, that is what I am trying to say. It goes partially like a square function or under root functions, and if you look at the GM CGS term, yeah, it does rise roughly linearly with VOV. Now if you want to maximize, GM by IDS gives what? GM by IDS gives you performance of the power, okay, that decides the power. Now if GM by IDS is one parameter of power as your spec, then there is an issue here. If you want to have GM IDS control and at the same time you want a higher bandwidth, so you want larger GM by CGS, now you have a problem. Larger GM CGS will have lower GM IDS and larger GM IDS will have lower GM CGS. That means there is some way optimization is going on, or optimal value is where they cross probably. So this VOV dash is somewhere where both are reasonable. Now this is not too good a value in fact. So can we push this curve up? Okay, if we can by some way, then we say okay, we have this VOV dash little better to control. Right now if this is very small, then control itself is very small. However, this has to be understood that VOV is, if it varies, we are really varying most of the performance of the circuit. So this should not be treated as good a design. If you use even a third figure of merit, which what I suggest sometimes, if you multiply GM CGS into GM IDS and call it, both you want to optimal, okay, multiply it and call it third figure of merit, okay. And if you see now, if I substitute those expressions of both GM by IDS and GM by CGS as 2 by VOV and this, it gives me an interesting expression which says 3mu by L square, okay. Mu is technology, okay, mu is technology, channel length is decided by technology nodes. However, that number you can change because I need not work on the shortest channel device or longest channel device, length can be in my control. Now this essentially is now trying to say that this figure of merit has nothing to do with the VOV, okay. So choice of VOV has now lost because you suddenly thought that if both are to be optimized, then you need not worry too much about, which is not true. In fact, how much current I will push will decide the gain, okay. So now the issue is that FM3 may essentially represent power and speed, but it does not talk of gain, okay. So VOV as a parameter, which we have been in so far talking in all my analysis so far, VGS minus VT is all that you may have to control, is not the best of design parameters, is that correct? And because of that I always suggest that this is not a fair deal. So let us see what we can do afterwards, and this is an issue which I thought as a designer you must keep in mind, that VOV is not the best design. There is no great correct expression between VOV and GM IDS, CGS into VOV, same is, there is no relation with strongly with any other parameters with VOV exact ones. So this is like a fudge factor, you are trying to fit somewhere and getting answers, okay. So what can be the other possible design spec or design parameter, and we will declare it little later, that which one should be actually used if possible, okay. Okay, So this fact which I said you that this is last time I should have showed you, this is from the last slides I should have showed you, but I just remember that this was not shown, so I thought you should remember that my VOV concentration is not really a great contribution. So we will see modify later that is that any other thing we can use as a parameter instead of VOV, okay, and that is why I am trying to show back this 2 slides which is that okay everyone? Yeah, but length I can always double it, triple it, I can do anything based on that. Okay, I can have let us say nanometer technology is 10 nanometer, 65 nanometer, I can put 130 nanometers also lengths. Okay, it is not that I cannot reduce then the technology node, I cannot pull it down to say for 65 nanometer I cannot have 45, actually 65 the channel length is not 65. Some other day in technology courses these numbers have nothing to do with channel lengths, okay. 45 nanometer has actually 25 nanometers channel lengths, 28 nanometers have actually 12 nanometers has channel length. So these numbers are also not very true, but these are called roughly you can say okay these are channel lengths, okay. So you can always go below up to the minimum channel length available for a technology, but you can double it, triple it, that number is in your hand, okay, is that okay? There are also issues in the short channel which I did not say, so I thought that today I will finish that part. In a short channel device, as I just now said, the lateral fields and velocity saturation effects both affect GM by IDS terms, okay. It is known that approximate expression which we used earlier for long channel can be modified for a short channel analog circuit performances. I write this current slightly modified by an expression which is 1 upon VOV by ECL, where EC is actually called critical field and it is different for different technology node. For example, for 0.25 it is 6 into 10 to the power 6 volt per centimeter, for 0.13 it is 1.5 to the 10 to the power 6 volt per centimeter. So if you see this, can you see from here ECL into VOV, ECL into V, what does that show, which kind of expression it is showing? If I substitute ECL here and I get this expression, what is it showing? Parallel combination of 2 terms, 1 upon ECL and 1 upon VOV. So now there is an addition, VOV we are only looking for, now there is an additional term in short channel has to be taken care, which is EC by L, EC into L, is that correct? Now this additional term will modify, and if I have done some calculation for a given value, typically if ECL is 2 volt for a VOV of 200 millivolt, the GM by IDS becomes 0.9 of the 2 by VOV term. So in a long channel what you would have used? 2 by VOV. In a short channel you may have to multiply it by 0.9, this is for one specific case. For a given technology, for given lengths, this EC has to be actually obtained and then used to find how much this coefficient should be 0.85, 0.8, 0.9, and therefore you can see now the GM IDS available at long channel is not available to you in short channel. Is that clear? So these are the design issues which as a designer we should keep in mind, okay.
Sir, what is this EC?
Okay, EC is a critical field where mobility starts actually strongly dependent on the fields, okay, strong dependence. Though mu is always function of E, but a stronger dependence when we say is called critical fields, okay.
And then you wrote 0.25 mu and 0.13 mu.
Yeah, for technology nodes. So for 130 nanometers this EC is 1.5 to, that's what I say, for a different technology node you will have to evaluate EC more accurately, okay, EC into L, okay, and that value you have to substitute there, so you find this constant factor will change for different technology nodes, okay. Is that?
This term is always there, 1 by each one, or is it?
No, this is true, this is to some extent till you go to very strong inversion or very weak inversion this expression is true, okay. But at least it has taken care of increased electric fields laterally, okay, which earlier we are not looking. So the additional field which we were talking about is now taken care through this term. Okay, VOV was not, we are assuming only channel from the top. Now we say okay, there is a additional source of charge can come. Okay, so this fact could be taken care in our analysis. Please remember some of these expressions are more what should say analytical expression. What does that mean? That I have derived under certain assumptions every time. Okay, so not all assumptions are true in all times. Okay, so in reality what should we do? We will see what can be done. Okay, but these are reasonable way of doing it. Why I am saying reasonable? Because at the end of the day you will work on some CAD tool which is like a SPICE for example. So where to start, at least you know correct guesses can be given to the input files. Okay, but this at least gives you some idea of physics, what has happened there. Is that clear? Some physics has been understood, that as you base there is an additional term may appear which will reduce GM by IDS, and this is very relevant in calculating why GM by IDS decide power for example. So now you can see power may actually have gone down, okay, or in some case gain may go down, whichever way we will look at it, we will see that part. So essentially unknowingly we actually thought that long channel expressions are good enough, but in 2012 I think that is not fair. So that is what I said few years ago, I never showed this, but now I thought you should all know that in real life things are changing and you must know more physics to bring closer to what can the experimental results show. However, I will tell you at the end this when I finish my design here, I will show you how exactly we should do in fact. Now I will actually give an example of a very simple amplifier which many times we are doing, but some values may be now given. Since our course has no formal tutorial as such, I thought at least some problems I will solve so that you will have idea of equivalent tutorial at least for 10% of my time. Let us say I have a simple MOS amplifier which is biased by a IDS current source, and the data given to me is the mu Cox value is 100 microampere. These are all random numbers, these are not specific in real life. Okay, so these are some contrived numbers. Channel length is 0.8 microns. So this is quite good long channel approximation. 0.8 is sufficiently long in channels. The hourly voltage is given to you as 50 volts. The technology first parameter alpha is 1.25. The load capacitance is essentially 0.1 puff. The bandwidth required for this amplifier is 2 megahertz, and I am expecting gain to be higher than 200. Trivials but important. So what are the specs? I repeat, the hourly voltage is 50 volt, channel length is 0.8, mu Cox is 100 microamps per volt square, alpha is 1.25. If alpha is not specified, what value you choose? 1. Okay, if alpha is specified, use that value. If not given, just use 1, or just do not use alpha anywhere then, essentially saying that. Okay, CL is 0.1 puff, bandwidth is 2 megahertz, gain greater than equal to 200. Okay, this is the spec given to us for a given technology node, and we want to find what can we find from there, what is the thing which has not been given to us and which is what we are designing. The size of the transistor, okay, that is the design. Length I know, but width, if I know my width, I get the design of transistor, and therefore I get all the specs to be available for actually performance. Okay, so that is fine. So for this simple amplifier, we can give its equivalent circuit. There is a CGS as the capacitance and CGD. Right now, since I have not specified anything on the CGS, my assumption therefore is 1 upon omega CGS at 2 megahertz is large enough to be open circuited. Okay, so I do not worry too much about, if I am given then use that. Okay, if I give you what is the value of CGS, you use that. Right now because I want to have simple solutions to show, so I neglect, because this frequency is higher, so I am not looking for, it is much more than 2 megahertz it will give bandwidths, so I am not looking for that value. Okay, this is a simple circuit this one can solve using Kirchhoff law. As I say, I like this nodal equations because spice solve most cases the relationship by node equations, but you can always use meshes. Okay, if you feel comfortable using mesh, you can do mesh analysis. If you feel comfortable with node analysis, you do node analysis. This is why I do node analysis, simply because spice does it, so you can also do it. I agree with, I want to hold CGD. CGS I removed, but CGD I want to show that there is a feedback. What is the issue on that? Okay. Typically CGS is higher compared to CGT. Okay. So CGD is a very, it's a series. So anything in series troubles you most. Okay, we will come back, that's what we Miller theorem we will talk about. That's anything in series feedback is an issue. Okay, anything across many times it can be neglected for the omega 1 upon this may be large enough, forget about it. Is that clear to you? This is not true for actual case. You may substitute and figure out, keep everyone. No? There is nothing that you have to remove or you have not to remove. You solve full circuit, terms will automatically get cancelled if they are smaller. Okay, you can't add 1 in 10 million, so what do you add there? So that term you can keep, so there is nothing wrong. To solve simple, I slightly took some assumptions. Okay. So if I solve this, I start from SCGD into Vn minus Vo minus GM minus V0 by R0. These are all currents at this node I am talking here. Okay, minus V by R0 minus SC0 V0 is 0. Then I connect the terms of Vn and V0. So Vn SCGD minus Gm minus V0 SCGD 1 upon R0 plus SC0 equal to 0. So you get an expression of gain which is V0 by Vn, which is minus Gm minus SCGD 1 upon R0 plus SCGD plus C0. Is that okay? Simple second layer, nothing more and nothing less. Okay. So why are we doing it? We want to solve using, there we gave only W values. Now I want to figure out, if given this data, what W I can get. Okay. If you can now see for a final expression. If I do this, take GMR0 out. Okay. What is GMR0? Minus GMR0 is the DC gain. Please remember, in analog circuit, the DC gain is not really DC input gain, it is a frequency independent gain. Is that word clear? It is called DC gain, which means without frequency whatever is the value is called DC gain. In fact, there is nothing, essentially I am not saying any input signal of AC I am getting a DC output, it is not statement that, but it is called DC gain. DC gain means at frequencies close to 0, whatever is the gain is called DC gain. Okay. It does not say input is DC, is that clear to you? So please get to this. So this is my DC gain into 1 minus SCGD upon this, and I have this now you can see C0 per CGD is the total load capacitance at the output, which has been given to us as how much? 0.1 puff. So this CGD value could have been given, C0 value could have been given. I just said that okay, whatever this sum total, this value is 0.1 puff. I am trying to reduce my calculations. In real life, you will have to use the actual values given to them at that point. Is that okay? This C0 plus CL, CGD I have used as a CL, and I say this is the value for the solving purpose. Okay. Now assuming, again to solve a very simple case, I assume that the 0 SCGD by GM is giving me a 0, that 0 frequency is far off, okay, away from the pole. So I just now even do not bother of it. Maybe it is relevant in some values, but now I am saying the CGD what he was worried about is such that the 0 is some 100 megahertz or 50 megahertz. So 2 megahertz is my bandwidth and my 0 is sitting at 100 megahertz. By then the gain has gone down to some 200 minus dB, so I am damn caring about it. Okay. So I am not worried about then when it starts rising, by the time it will come to 0 it will be million years. Okay. So I don't care if the 0 is far away, and in design, and that is the game you will play, in design see to it that your 0 is far away from your any number of poles you are looking at. What is the advantage of that? That because it is going to give you some plus phases and you are trying to adjust phase margins in actually amplifiers, this should not be the bothering point for you, okay. And that is one spec I will use, that okay, the 0 has to be at least 10 times this, and I use this value itself to calculate, okay. So 0 is something which we do not want very much, because 0 gain is not worthwhile, so that fact should occur far away from us, okay. However, 0 has an advantage. What is the advantage? If the same position 0 occurs at the pole, then it will cancel, so your gain will become flat anyway. So 0 is not that bad either, okay. But right now let us see what is going to happen. So this is possible in most cases, as I say 0 and this is possible in most cases, as normally R0s are much higher than GMs, okay, 1 upon GMs. This value which I am saying, this is a condition which is normally made, so 0 may come normally far away, but not necessarily, because CG may decide where it will come, okay. As I said, this is a solution for the sake of design, and these are not any specific technology rules. So now I have some expression from this, I have neglected 0, so I got AVS is AV0 1 plus SR0 CL. Now what is the bandwidth from this expression? 1 upon R0 CL, omega minus 3 dB as it is called, if you wish, the definition in Bode's diagram, okay. Then this is 1 upon R0 CL, the DC gain is minus GMR0, the gain bandwidth product is GM by CL. Now these are the expressions which I can use in my design for evaluation of what? The width. All that is width, my interest is in widths, okay. Is that expression you wrote, these are the expression I will use, the bandwidth which is 1 upon R0 CL, the DC gain is minus GMR0, and the bandwidth is gain bandwidth product is GM by CL. Now using these expressions we can now solve our problem, what data I have given. I could have directly started on this, but I thought I will give you expression first and then show you where do I substitute, okay. Is that 3 expressions clear? Only 3 things I am talking about, gain bandwidth, bandwidth and gain, that is what it is, okay. Okay, so if I substitute, now it is a constant current source as bias, which expression I should use? I am fixing IDS, 2 beta IDS, a under root of that is that, see that chart in which I showed which one I am fixing, which is the center one I am using. So I am now using GM. Is that clear? That day I gave you table for 3 fixing. In this case this is the middle one which I used, in which IDS is getting fixed, okay. So GM is 2 upon 2 beta by alpha. If alpha is 1 you may not use it, but here I have given you, so 2 beta by alpha IDS, and we also know R0 is hourly voltage divided by IDS, okay. So these are additional expressions, 3 first I said, and these 2 more important expressions I have to use in my design. Since I have said the bandwidth is 1 upon R0 CL, what is the bandwidth? 1 upon R0S, so the frequency which is 2 pi f is the angular frequency, so actual frequency is 2 megahertz given to you. So you say from that expression R0 is 2 pi the bandwidth into CL, I know bandwidth given to me is 2 megahertz and I am given the load capacitance of 0.1 puff, okay. So I substituted everything here, so I get a value of R0. So what is the value of R0 I got? 0.8 mega ohms, is that okay? This is 2 pi bandwidth into load, okay. That expression we just wrote, we are just substituting values now. So the first thing I figure it out that the output load for my case is 0.8 megahertz, and they mega coming from which parameter? The bandwidth. Since we are given bandwidth to me, I figure it out that it should have this much as R0. Now I want to evaluate IDS, okay, because IDS is going to decide GM, so I must know my IDS, but I know IDS, this IDS is nothing but early voltage by R0, okay, which is 50 by, from where this expression is coming? The slope into this is the voltage, so this is the from the slope characteristics. So I evaluate IDS equal to 62.5 microamps. As I said, these numbers are not sacrosanct, these are very arbitrarily chosen values. Please take it, the real numbers may be very different, it may be actually milliamps or tens, hundreds, 800 microamps kind of thing. So right now do not go by this, oh you said 60, 60 is some arbitrary number. I also know my AV0, which is GMR0 as the magnitude. I just calculate GM, which is gain divided by R0. You have been told that okay, instead of 200 I use higher, you said, so this 240 only to divide by 8, nothing great, you can choose any other value. So 240 by 0.8 10 power 6, this gives me GM of 300 microsiemens, okay. Is that okay? Please remember you said greater than 200, so 240 is greater than 200, it is not 300, so it is not too high also, okay. Of course you can use 200 value here and get whatever value, but that is the minimum point you are, this is higher, I used it. So if GM, I already written an expression, what is GM expression? 2 mu Cox by alpha into W by L into IDS, is that correct? Under root of course. So from here I can figure it out, what is the value of W by L. So W by L is GM square alpha upon 2 mu Cox IDS, is that okay? Just manipulate. Substitute all values, GM square 1.2 as alpha, 2 into mu Cox is 100 into 10 to the power minus 6 and IDS is 62 microamps, okay. So what is the final result coming out of this all calculations? W by L is 9 roughly, accurately you may find, but this is roughly. I am very sorry. Okay, so since the length is 0.8, check it whether that is 0.9 also, okay. I mean I just roughly did this and maybe wrong also, but just, so essentially W is now figured out for what are the values we met, the bandwidth of 2 megahertz, gain greater than 200, driving a load capacitance of 0.1 puff with a given technology of channel length of 0.8 with mu Cox beta value given to us as these numbers. So I have been given a specification and I have designed the amplifier value, okay. This is how you design. So it is the inverse process, as I said, start looking what is given, start looking expressions, substitute properly and get the what is not known to you, okay.
Because it was current source.
Yeah, biased, strong fixed current source, okay. I can put something to bias by VGS also. I put 2 resistors across the gate and can give a gate bias as such, okay. I can do many way, I can also push from the lower side the source current, syn current which is through mirror, okay. So there are a number of ways in which I can play this game, but as of now I say okay, this is the, okay, in this calculation you must have seen in real life, if this resistance of the current source is not infinite, where it will appear in the circuit base, if that has some RO base, another RO parallel will come from the load side, okay. This has to be understood. In this case constant current source with ideality is used. As I said, the idea is around 0.35 down you should use short channel effects, okay. But people have used long channel devices, models even at 0.25 also. But why we are not worried too much about, because when you go on a SPICE for a given technology the models are available for that technology in the SPICE itself. So I am not really looking into what model I, but analytically up to where I should use expressions. So I say okay, in most cases up to 0.25 you can use these analytical expressions. At the end you are finally going to simulate on SPICE, and that for a given technology node will be able to take care of the actual models of that technology. Okay. So we are not too much worried about models, but since I want to know where do I start, I must know reasonably good initial models so that I can give you a good initial guess. Is that clear to you? So this issue has nothing to do with actual SPICE simulations, okay, because SPICE will take care of different models at different nodes, okay, and then it will use different analog models, it will use different RF models, it will use different digital models. So it has all kinds of programs which it will take care. Okay. So in my opinion, for this design the GM by IDS is 4.8 per volt. Now let us say someone says that I want a low power design for the same amplifier. Okay. So what does that mean? I want to reduce IDS, is that clear? If someone says I want to design an amplifier for a low power comparatively, right now what is the power? This IDS into VDD, which I have not specified, but that is the power dissipation. So I say okay, I reduce power means I reduce the IDS value itself. Now what will happen? If we see an expression now, the width is proportional to 1 upon VO. I have given those expressions, please wait, I have given enough expressions for W's and everything, and W is directly proportional to GM by IDS. Okay. Now this, if I use lower IDS, which is what low power people are asking me, I need from this expression width will be larger. Is that clear? Is the design issue clear? If someone says reduce IDS, essentially I am saying increase widths. Okay. Is that okay? So what is the penalty I am paying? Area. But that person may say no, it should have a smaller area. Then I have an issue, because you say I want a design which has low power and low area. Is that point issue clear? I reduce IDS, W may increase, I may meet the spec. But now he said no, I cannot give area. So what do I lose in case I do not want to lose area either? Okay.
If we increase W, the current decreases.
If I reduce IDS, W is proportional to GM by IDS and fixed GM. Okay, the GM has to be fixed. The reason why I want to GM fix, because gain has something to do with that. So I do not want to hit GM. Otherwise IDS is going to hit GM as well. Okay, you can see IDS is under root beta into IDS. So if I reduce IDS, this will GM will go down, but I will adjust W by L to get that GM. So I am fixing GM, and they say okay, I reduce IDS, so that the power is only related to IDS. So I say okay, pull down that. As soon as I pull down that, I will have to increase W, because to beta IDS, if IDS reduce, beta must improve, that means width must increase. Is that okay? Since width increases means area increased, but spec says no, reduced area. You understood the design part, what I am going, why I am showing you all this, because as a designer these are the issues which will come before you. Okay. This can be actually done by an optimization. You can keep changing two values till you get reasonable area and reasonable power. Okay. However, the models available to you are only long channel models, and we say these are not the ideal models. Okay. So how do I optimize? That is the actual design. Is that point issue? But CL has nothing to do with W by L. But that CGD is very small compared to the output load. The other load is driving something which I do not know, I just put it 0.1 value. See, the load is not the part of the circuit, load is from externally you are putting. It can be any value, any driving you have to do. Op-amp may drive any load, for example, the slew rate may change, but that is the way it is. I may design for worst driving situations, but load can be anything, it is not, it is plus CGD, I agree with you, but CGD is a function of W, that I appreciate, but this other values of external load CO I am going to put, can be any value, okay. And to save myself I am saying okay, even if that varies, the C0 is stronger than the CGT increase.
But in a larger circuit, if you connect resistors, then the load capacitance will be.
Because the next W bar I don't know, no, the next stage which I am driving, I don't know what is it, it's a ATD inverter input or a space switch capacitor filter input, I don't know what W bars they are asking for their input side. So I am only saying that whatever it is, equivalent capacitance I have to drive is so much, is that clear? I am not trying to say that this is the final answer, I am just trying to give an method of looking things, is that correct? As a designer, how do I look into it? Okay. Okay. This can be actually done by optimization, however long channel models may not then suffice, that is our issue, is that okay? So just now I said if we have a design for a smaller area and smaller power, we have a trade-off situation available. For lower power we reduce IDS as we say, hence for a fixed GM, that means gain constant, GM by IDS increases, because if IDS reduces, GM by IDS increases. Since VOV is 1 upon VO is proportional to GM by IDS, VO will occur, reduction in VOV will occur at lower IDS, but W is inversely proportional to VOV, so W increases. So increase of area is whatever you look, you always see W is increasing. Now how to get rid of such situation, because these models are, so I will worry is this linearly going or is it some other law it is following, okay. If that's so, then it will not proportionately increase, is that clear? So I want to see is that model which I use for VOV is an ideal model, though I may not have better model immediately, but at least can I do some mischief to actually get rid of this situation, is that point? W is, whatever we do, W is increasing. Okay, so this, all that I said earlier is the statement written by me here, nothing more than that, okay. Whatever I said earlier is the written part, an actual language part I wrote here, so that at the end what I said is available for you to read. So what is the actual values or what is the accuracy you should build to doing this is what my next is in design. So what do we do now? In real life, don't use VOV as your design parameter, use GM by IDS as your design parameter. This is slightly different from most books which they talk, I am not saying all books, most books they always go by VOV terms, or they are called VXS, some called VGS, VGT, books name different, but this is slightly different, though please remember they are connected, it is not that I am going physics out, okay. So I say okay, from the expressions I have, for a real device, for a given technology node say 0.25, 0.35, 90 whatever it is, I actually do spice simulations. For different GM IDS, I evaluate different IDS by W, okay, and plot it, is that okay? This it can be done even experimentally by technologists and by simulation by designers. Sometimes this technology people will give you this graph. What is that I am plotting? IDS by W as a function of my design parameter now is GM by IDS, okay, is that clear to you? So some random numbers are not really random, this is typical values for these technologies, so 0 to 20 Siemens, and I plot microamp by micron on this side. So I say we know it, smaller the GM by IDS, IDS by W will be smaller, and larger this I get W, is that clear to you? So this figure I actually can either using SPICE or using technology data if provided to you, evaluate this. This is a major start work before, once you use this, also use it for different channel lengths. You create this graph for you, is that clear, which is your base design this. You do not have to do n times, for a given this you do once, both for different channel lengths. If you are going to use multiple channel length devices, for each of them you create these graphs. Okay, instead of plotting this graph in that fashion, if I plot logarithmic 0, 10, 100, okay, or 1 10 to power 1, 10, 100 on a log scale against GMIDS, it may look more like linear graph. You must know how logarithmic term behaves, okay, not exactly linear but close to linear. Now for that earlier problem which I said, I have solved that GM by IDS was 4.8 per volt, okay. So I go on this graph. For this GM by IDS, I actually figure out what is IDS by W. Is that clear? So for example, in this some number I chose which may not be accurate again. So let us say for 4.8 this value is 40 microamp per micron. This I do not say exactly some number, it can be 45, it can be 38, it can be 30, but some number. So for GM IDS of this I have figured out IDS by W is this number, but IDS we are having earlier was 62.5 microamp from that design. So I got now it is only 1.56 microns. So if you realize that the decision of getting actual W's, if you have only used VOV expression, you have over designed the chip. W इतना बड़ा लग दिया, अच्छा तो हो जाता है but एरिया खा जाएगा. Of course these are not, as I said, don't take it exact numbers, this may be not 1 point, actual reason may be 4 microns, 3 microns. Is that clear to you? This number which I am only putting from graph, but this may certainly always be lesser than that earlier VOV model. So the first time I told you that don't use VOV model, use GMIDS model, okay. And if you use this, your bits will be much more controllable or much more known to you, which may be having lower areas than what you thought. Is that correct? So ये आपको फर्स्ट टाइम मैं इस ऐसे क्लास में बता रहा हूँ कि GMIDS जो है वो एक्चुअल डिज़ाइन पैरामीटर होना चाहिए, इट्स नॉट VOV. All these years I have been teaching a course and say VOV. So this year I thought I will change my track and I say okay, don't use VOV, use GMIDS. But then I figure out I don't have IDS bias, so actually plot, okay, and from that plot you can get your correct bits. Is that okay? So this is a better way of looking at design than the VOV models. Now in this case I am not very much worried because SPICE will have models, okay. So these graphs can be more accurate to a given node than what the actual VOV models I have derived, okay. So in that sense I am more correctly doing things which probably will come into real life, okay. So as a designer, what is the best way of designing? Copy someone's, but that is plagiarism, so don't do that. So what else you can do? Do this, okay. Is that okay? So this is, as I keep telling you that once I said you that every year I change my track. So this year I am changing my track to saying it is IDS, GM by IDS as a parameter of design. Though please remember 2 IDS by VOV is GM, so I am not really going out of physics. Relationships are similar but not the same as I just showed you. Is that clear? Because it now is taking care of the real life situations in the device. Is that clear? That 0.9 also then you don't have to worry too much, because this will take care of all such things which could probably occur. Is that clear? Okay. The second amplifier of my interest, the first amplifier I said the gain is GM times R0 and gain bandwidth is GM by C. Is that correct? So if I want to increase the, what is GBW? Gain bandwidth product, which is GM by C. So if I now take a system in which I want a larger gain, one method is I can design a single amplifier with larger gain, that is also possible. But the problem there is it will have two huge values of W bias, okay. It is called the aspect ratio will be very bad for you in actual designs. So what is the most common practice of doing designs is to put cascade of 2 amplifiers. You want 100, make 2 10 gain amplifiers and cascade them. Cascade means output of first is given to the input of the next, okay. Let us say each has a gain of A1 A2 which is GM1 RO1 GM2 RO2. So the gain is GM1 GM2 RO1 RO2, and if they are equal GM square RO square is the gain. However, the bandwidth is gain bandwidth divided by A0. So what does that mean? If I increase the gain, my bandwidth is going to be lower now, okay. So cascade amplifier has, yeah, I do increase my gain, but I have a problem of losing the bandwidth across. But that is what we do not need. In most designs what will require, or most system what will require, I do not want to lose my gain bandwidth, okay. I want to keep my bandwidth same, okay, but I want to boost the gain. This gain bandwidth product is called figure of merit. Why it is called figure? For a given this GM by C, for a given IDS, given capacitance, says this is fixed, it is like an FT value equivalent of that, okay. So that is a figure of merit. Now this figure of merit is, that means sacrosanct, technology के लिए, power supply के लिए यही fixed है. But designers cannot go by saying that I cannot increase gain without losing bandwidth. If they say so, then there is no design left, okay. So क्या करते हैं? So the alternative to this cascading, the word we use is, amplifier we use is called cascade amplifier. So our need is not to reduce bandwidth but to improve gain. Cascade does not do that. We figured out that another way of looking at the same thing, and we call that as a cascade amplifier which allows us to retain bandwidths but push the gains. What does that mean? You have broken the technology figure of merit, gain bandwidth product is constant, you said, now I am breaking that. You said, अरे तो fixed है कैसे करेंगे? Now I am trying to see, I will boost the gain but I will not lose my bandwidths. Is that clear? A typical cascade amplifier is shown here. Just forget about M2 first, so it will be a normal amplifier. M1 is the driver and IDS is the bias current source. So if I have M1 this and I interpose a transistor M2 in series, okay. Though cascade amplifiers have their own problems which we shall see later, but there are folded cascade op amps available, OTAs available, so this process is very nice, okay. What is this? What is source is grounded, so which amplification it is doing? Common source. To this M2 I am giving a fixed DC bias. What does my fixed DC bias means? For AC what is that terminal? Ground. Fixed DC means ground. So what is that amplifier is what kind? Common gate amplifier. So I have a common source amplifier getting in next stage is common gate. In cascade I have both common source. The first time it changed from common source to next stage is common gate. Is that okay? What is the difference between the two? Both stages in cascade was common source. Here common source is followed by common gate, okay, and that helps to improve gain but not lose. That is exactly what cascade is all about. If this is what your circuit is, equivalently saying, okay, assuming right now C's are internal C's are not used, equivalently saying I want a cascade amplifier which has a current source as GM effective Vn shunted by RO effective and of course the load capacitance. Is that okay? This is what I am looking. So the AV0 will be GM effective into RO effective. Now if GM changes, what will change? The bandwidth will change, gain bandwidth product will vary on that. Whereas if GM does not change but only RO improves, then I have boosted the gain without getting out of bandwidth issue. I am getting out of bandwidth issue. Is that clear? So I may like to do a design for this amplifier in which GM may remain almost constant, almost a little bit this, but RO may boost my orders as much as I want actually. Okay, that is what the theory of cascade amplifiers is. The worry as a designer, which will solve this problem soon, is something like this. In analog circuit, what is the guarantee of each transistor region? All theory were derived on what basis? The transistor is always in saturation. Is that clear to you? So there will be a VD sat here or VDS drop here. There will be a VDS drop here. And if this current source is replaced by similar two p channel transistors, there will be two VDS drop upwards also. Okay. So from the power supply to the ground, how much voltage now I will have to drop? 4 VDS. If I want a little more, I may put another series in that, I may require 6 VDS. The minimum VDS we shall see later is close to VT to make transistor in saturation, which essentially means that now you are closing VDD, either you improve your VDD further so that all remain to this, or some transistor will come out of saturation. So cascade started fantastically in theory, but in real life our worry started as chain increased in series. Okay. This is like a NAND gate situation. If you are larger fan in kind of NAND gates, the issue is too much capacitance comes and too much current drops have to be given, because that each will have to be then turned on. Okay. Speed anyway goes away. Okay. So it reduces all your other hardware. Okay. So the NAND gate function is similar to what here we are now saying, that too many in series, please take it, every time I do it I push it by gain. I put another one, I will put another gain on that. Okay. But if I put too many, my worries are the transistor will not remain in saturation for a given VDD. Okay. So there will be some limitation of maximum GMR0 which I can attain even in cascade for a given technology nodes. Okay. So it is not that you can increase this to any number. Okay. You are limited by, so थोड़ा सा modification कर सकते हैं, उसको बोलते हैं folded cascade. Okay. So we tricks. Okay. But it reduces one VDS down, that 4 होगा तो 3 हो जाएगा, but still it is not small. Okay. As much you put, additional power supply voltage either is required or you can no more than this chain is possible. Okay. So there is a limited gain increase, but the gain advantage is your bandwidth, gain bandwidth product is retained. Okay. That is exactly what we are trying to do in cascade. For an AC case, this is my V in, this is grounded, this is VO1, this is VO2. This is equivalent of AC. Okay. Now what we say, let us say the current flowing through this small AC signal for a Vn is small I. Okay. So we say for this transistor M1 and this transistor M2, so let us say for M1 now I is equal to how, what I should write? Yes, GM1 Vn, okay, plus VO1 by RO1. Equivalent circuit, two current sources, one GM, other V by R, so two current sources in parallel, that is the net current at the drain side. Is that clear? Now what I do is, I actually want to do something in which I will say, if I say GM and I say I upon Vn at VO1 is 0 for the first case. But if I do for the other, let us say this is I1, though I1 I2 is same, so GM1, okay. Similarly I can write I2, what is I2? GM2 into how much? No, just think of it, how much is VGS there? Minus VO1, 0, please remember the VGS for this is this. So 0 minus VO1 is the VGS for that. So 0 minus VO1. Is that okay? What is the current in this? Plus GO2 into VO2. Is that clear? Is it okay? So now I figure out, oh sorry sir, you are right, you are perfectly right, VDS, I am very sorry, okay, you are perfectly right. RO is GO2, okay, 1 upon RO is GO. So now what I say, if I have these expressions and I can now say for any amplifier, GM is defined as, if I ground VO2, okay, if I ground VO2, then what will happen? Ground means for AC. So the current is only proportional to Vn, which means GM is I by Vn. Please remember, current in a circuit is still same. Is that clear? Current in a circuit cannot be 2. So we say I is constant, which is flowing through both M1 and M2. So now GM is only given by, sorry, VO2. If I say GM effective, as I say, I should not say this is GM effective. GM effective is I by Vn when V0 is shorted. By similar argument, what is GO effective will be? Yes, I by VO2 when Vn is grounded. When input is shorted, impedance seen at the output node is the output impedance, is that correct? So all that now I have to figure out a relationship between I1 and I2 from this such that I can derive GM effective and GO effective, and once I get what is the thing I am getting, GM R0 is the net cascade gain, is that clear to you, and that I'll GM by C. If GM effective comes to be same as GM1, let us say, then my gain bandwidth is not changing because GM by C, is that clear? But at the same time gain is boosted because gain will become, oh okay, so I will tell you RO2 or RO effective will be GM1 RO1 times RO2 roughly. What is this? What is GM RO1? The gain of the M1 multiplied by the output resistance of the second will be the RO, will derive this. I am just giving you hints on that because this time is running out, so I just did not want to derive it. So the gain in cascade is that I somehow want to push RO higher but retain GM as what it was, okay. So I will beat that technology constraint and I will say okay, I got what you are really looking for. In theory what we are doing is the following. Normally what we will do is, if this is your amplifier, okay, this is your gain bandwidth product, if I increase the gain really, I will get this curve. If I boost the gain A0 to A0 dash, my this point G gain 1 will move to gain bandwidth 2, which is smaller. This is what will happen in cascades, okay. So what do I am now really looking for? I may do this, okay. I am trying to do this, I still reach the same point, I improve to some extent the bandwidth, and I also improve my gain. This is what cascode does, okay. This is what cascode is trying to do. Is that clear? That is why cascode amplifiers are ideally suited for analog applications. But what is the catch in cascode, as I said, we will discuss in next more detail, that the VDS adjustments becomes very crucial, okay. Typically VT is not now equal to 5 times VDS is not 5 times VT. Earlier we used to have 1 volt VT, 5 volt VDD. Now 0.4 volt VT and 1 volt VDD. So only 2.5 times. So if I want 4 VT drops, it is 1.6 volt supply is required, where I have only 1 volt or 1.2 volt supply. So now I am constrained that I cannot use cascode at random because my VDS situation may be not very conducive to me. Is that clear to you? Otherwise, theory wise, it seems to me I should just forget cascading and use everywhere cascodes. Okay. See you then next time.